Good day, folks. This is tutorial number 9, which is closely related to tutorial 8. It deals with a situation where the torque is to be calculated when we are given the angular acceleration. This is all these tutorials all belong to a playlist which is called Dynamic Scenario and Animation in 3D Experience. And let's see now, what is it that we did in tutorial 8? It's the same geometry, same dimension. What we don't know is the torque needed to turn this disk by given angular acceleration, as you'll see in a minute. Steel is used for material properties, and the mass of that disk is 152.6 kilogram. And based on elementary formulas that you can find in any dynamics books, I axial and I transverse are given by these two numbers. And we're going to do a 10-second simulation. Now, we are given the angular acceleration of the disk. Now, because of that, we can find the angular velocity of it by integrating this, and it's going to give you 41.95 times t. Okay, so the integral of a constant is that constant times t, and that's what I have here. Now, you can plot it, and this is exactly the same data that I used in tutorial 8. Now, based on that, if you take that angular acceleration and multiply it by I-axial, because this is rotating about the axial direction, you're going to get a torque which is here. So that torque came out to be a constant of 200 Newton meter. Okay, this was in tutorial 8. But you can plug in these numbers, you can plug in this and that, you're going to get 200. Now, in view of the fact that I'm given angular acceleration, quote unquote, velocity distribution, angular velocity, you cannot just go and repeat the steps that we did in number 8. What you have to do is you have to create a revolute joint, make sure that the angle is being controlled there. And once you do that, then you can apply that angular speed on this revolute joint and simulate it and extract the torque by plotting at the end the internal torque about the axis that we want. That's pretty much different. We did not have to create any joints in tutorial 8. Now, here's what I mean. You have to specify velocity, law excitation, and when you do that, you just click in, you just right click and say edit formula, and you go to the formula and plot and type in exactly like what you had. 41.95 rad per second squared times time, and then run it. Okay, so let's go ahead and do that. Uh, Here is 3D experience. Let's go to the platform interface, so assembly design. First of all, make the stand here. Right click insert 3D part. Okay, let me call this thing the stand. Right click properties, stand. This is going to be stationary. It's not going to move. Stand and stand. Okay, let's go make it. Just a cylinder. That's the way I do it. On that plane, I will sketch a circle. Let me give a dimension here, although it's not moving, but I would like to have a control of what I'm doing. So maybe I'll make it point, what is that? This is diameter, I'll make it point 4, okay? Good. And then exit, and then pad it a little bit more, just so that it looks nicer, maybe by point 05. Too many zeros, too many dots here. 05. So there we are. So this is going to be our stand. Now we insert our actual disk. So right click insert 3D part. Let me call this thing disk. Okay, let's go make it. So on that plane, I will sketch. Well, I know the circle, the diameter of it is 0.5, 0.5, okay, and the exit, and the height of it is 0.1. Oops, the other direction though. Flip it. Okay, good. So what we have here, this top disk is what is 30. The bottom one is just the stand. Okay, good. Now, all the way to the top. Oh, by the way, since I'm going to be plotting some stuff, I might as well just create a point on that while we're in this part. While we're in this part, let me create a point, uh, say on a curve. It doesn't matter where on that curve, anywhere. Say OK. So a point has been created here all the way to the top. Now let's create our revolute joint. First of all, the bottom, namely the stand, is going to be fixed. So we are in assembly design. Let me fix the stand. Do I do that? Okay, the stand is fixed. Then I'm going to create a revolute. These are the templates. I'm going to use the one here. Axis, axis, plane, plane, and then angle between them. Okay, so I'm going to use this. So this axis and the bottom axis, this plane and that plane, and this is the one that I'm saying control. You have to, you need to have a command here. So this item that you see in there, right here, make sure that the angle is control. So what I mean by that is the angle between two vertical plane. So it doesn't matter which one, this one from, for example, one of the parts, which is the disk, and the same one if you want from the other one. It doesn't matter. YZ, it can be a different one. The angle between these is controlled. This can be XZ, XZ, or YZ, YZ, or XZ, YZ, the other. And this is controlled. Right now, of course, there's 90 degrees, that's fine. All right, so what we did, we created a, this is going to be a revolute. Okay, good. Now we are going to go to our mechanical system design, create a mechanism, okay? And let's check the joints. There is going to be a fixed one and a revolute one, and degree of freedom is 1 because this one we are controlling the angle. Fine. Now let's apply materials to it. So here's the weight definition. Click on it. Or you can put it on the entire assembly, or you can put it on these individually. It doesn't matter. So I'm going to put it on the entire assembly. Click on this link. We're using the properties of steel, so I'm going to check this box here. See that, this box over there? And it's going to put the properties of steel. And based on the properties of steel, you can figure out who's who. For example, if you select this guy, later on it's going to give you the mass of that. We're going to check that actually. This is the total. This is fine. Okay, but let's check something. If I click on the stand, that's going to give you the mass of the stand, which I don't care. And this one is the mass of the disk, which is 152.5, which is exactly what I had in there, 152.5. Okay, good. So we have actually materials specified on this thing. And that's pretty much it. So now we're going to go to the mechanical systems experience. We don't have to create a mechanism, it's already done for us. We're creating a simulation. Okay, now here's what we're going to do is velocity excitation. See that? Velocity excitation. The support is going to be that command. That's why I had to control it. Otherwise, I can't pick this. Now, because there were no joints and commands in tutorial 8, I couldn't do something like this. I mean, it just didn't make sense. I didn't know what this thing was. Now I know. You click on it, okay? And here you click on f of x and you go and type your stuff. So if you go back here, what you want to say is that omega equal to 41.95, this is rad per second squared times time, okay? And that's what this is. So I go here, 41, 45, what was it, 49? Can't remember. 41.95. Put this thing in parentheses. Actually, that's fine. 41.95.95 rad per second squared. I'm going to change this thing to rad because my units are my default units were in turn per minute, but this is going to be rad per second times. If you feel more comfortable, you can put it in parentheses, but I don't think you need it. Second squared, not second. Second squared means S2. That's a big mistake. S2. Otherwise, you come back and units saying units are not homogeneous. 41.95 rad underscore S2 times time. And then we say OK. And then we say OK. So a formula has been created here. And if you double click on this, and if you go to f of x here, see that f of x? You click on it. It'll take you to that formula. If you want, you can make changes, etc. Now, that's pretty much it. So you go and create your dynamic scenario. Or let's actually create a probe to cancel that. Here is a probe on that point that I created here, on that point, so that I can track the stuff for that point. Okay, now, dynamic scenario, velocity excitation was created, the probe was created, the total duration is 10. Say okay. All right, and now we're going to run it. 10 seconds. This is turning at that angular acceleration. Because its angular acceleration is constant, the torque will be constant. It better be 200. Okay, let's when it finishes, let's go and plot some stuff. So we go view scenario results. Just give it a minute. Okay, deselect all. First of all, if I do angular acceleration, I better get 41.95. So angular acceleration, what is that? 41.95, right there. That's correct. Let's go and plot the velocity. Plot the velocity, angular velocity about this. You better give me that linear rise. And because my units in turn per minute, this is going to be 4,000 RPM. Okay. And finally, if you look at the torque, remember our interest was to find the torque specification, and we go here and say internal torque about the z-axis. Better be 200, right there. Okay, so that takes care of this tutorial, and good luck.